Okay, let's look at example 2 now. It says use the first derivative test to locate all local extrema for this function. And then we're going to plug the x values of the critical points back into the function to get the y values at the extrema. So we're going to apply the first derivative test. So the first derivative test says that if there is a relative maximum or minimum, it's at a critical point. And so we need to find the first derivative and then evaluate where it equals 0 and where it is undefined, but the function is defined. That second part's super important. Don't forget it. So we're going to take our function f of x, and we're going to find the derivative. Remember to freeze the inside when you're doing the chain rule. And then when we take 1/3 minus 3/3, we get a negative 2/3. And then the derivative of the inside, of course, the derivative of x is 1, derivative of -1 is 0, so multiplied by 1. So we can write this a couple of different ways. We can write it like this, or we can drop the part with the negative exponent to the denominator. So the only thing left in the numerator would be the placeholder 1, and this would be x minus 1 raised to the 2/3 power. Now, remember that the 2/3 power is the same thing as the cube root of x minus 1 squared, all right? And since it's a cube root, we don't have to worry about negatives underneath the radical. Now, keep in mind that the original domain, which is important in order to know whether or not the function is defined, the original domain is based on the original function, which is itself a cube root. So it's the cube root of x minus 1, but cube roots are defined everywhere. So the domain for the original function is all reals. So there are no restrictions on where the original function is defined. So now we're going to look for our type 1s and our type 2s. So our type 1 is when the first derivative is equal to 0. Now, unfortunately, when we put it in this form, it's very easy to see that because the numerator is a 1, it's never going to be equal to 0. You can't set 1 equal to 0 and expect to get anything. It's not true. It's false. So there's no way to make this expression here into something equal to 0. When a fraction is there, the numerator has to be 0 and the denominator not 0 in order to get 0. And we can't make 1 0. So there are none of type 1, which is unusual and probably one of the first times we've seen this. And now we're going to look for a type 2 critical point. These are critical values or critical points, type 1 and type 2. And now we're going to look for type 2, which is the first derivative does not exist, but the function does exist. So it's got to be in the domain, but the derivative does not exist. So f prime of x does not exist, but in the domain of f. Okay, so it's got to be in the domain of f, which our domain of f is all reals. And then we look at the first derivative and we say, is there a value that would make the denominator equal to 0? And of course there is. When this got moved to the denominator, that meant that x could not be 1. So we do have a type 2 critical point here. So our type 2 critical point is at x equal to 1. So now what we need to do is divide up the real number line. We only got one critical value. So that's going to divide the real number line into 2 sections, basically to the left of 1 and to the right of 1. So we're going to take a test point on either side of the critical value. A decent number that is to the left of 1 would be 0. And I like to circle my test points. And a good number to the right of 1 would be 2. Okay, so when we're looking at this one, we're just going to test it into the first derivative, and we're really looking for the sign. We are not looking for the actual value. We're looking for the sign. Is it positive or is it negative? So when we plug it into the derivative, notice what happens because of the format of the first derivative. This is a cube root which is being squared, and since it's being squared, what does that tell you about the sign?
It will always be positive.
Very good. It will always be positive. So one is correct. We're going to have a positive at that value and a positive at that value, which means the first derivative doesn't change sign. So it's going uphill, and then it has a point where it's not defined, and then it goes uphill again. What does that tell you about relative extrema? Do you have any?
Saddle point?
Could be a saddle point. It could be a saddle point, or it could be some kind of point where it's a corner or a cusp or something like that, but it keeps going up. Let's take a look at the graph. Or it could be a vertical tangency point. Okay, so it could be any of those. So let me get all of these off of here. So we're looking at the graph of y equal x minus 1 to the 1 divided by 3. There we go. So at 1, which is our critical value, what do you have there that's causing the first derivative not to exist? What's happening right here? Yeah, you've got a vertical tangency point. So we've got a point of vertical tangency, which causes the first derivative not to exist, but obviously the function does exist. But notice how it's increasing to the left and it's still increasing to the right. So we do not have a relative extrema there. However, what else do you notice about this? Alluding to what's coming in the second derivative, what do you see that changes right here when x is equal to 1? What is changing?
The direction of the concave.
Yes, the direction of the concavity. So it's concave up from negative infinity up to 1, and it's concave down from 1 to infinity. So we do have something there. It's a change in concavity, but we do not have a relative extrema. Okay. So we did not find any relative extrema on that one. No relative extrema. If there's no change in the sign of the first derivative, there cannot be a relative extrema there. It could be a point of vertical tangency, something else like that, or it's a saddle point. Okay, let's take a look now at example 3. Use the first derivative test to locate all the local extrema for this function, but only over the interval from closed -4 to open 4. Remember to plug the x values back in to the function of the x values of the critical points that are places of relative extrema to get the values at the relative extrema. So again, we're looking at our function. So I'm going to rewrite the function here. X squared over x squared minus 1. Now, if we look at this one, we need to think about what the domain is because we're preparing for a type 2. So when we look at the domain, we may want to think of this as x squared over x minus 1 times x plus 1, which means basically that our domain will be all reals except for 1 and -1. We will not be allowed to have 1 or -1 in the original function because it causes the denominator to be 0. So 1 and -1 are not in our domain at all. So they cannot be critical values. We cannot have relative extrema there. They're not graphed. When you graph, there is no point at 1 or -1. And both of those values are in the interval that we're looking at from -4 to 4. So we're going to need to be careful about that. So the first thing we do is we look for our critical values. We have type 1, first derivative equals 0. Type 2, first derivative does not exist, but it is in the domain of the function. So I'm going to do, I think I'm just going to do the quotient rule, but on the original, not on the factored form. So this is going to be f prime g minus g prime f over g squared, where the numerator is the new f and the denominator is g. So this is going to be 2x times x squared minus 1 minus the derivative of the denominator is also 2x, and the numerator is x squared, all over x squared minus 1 squared. So this would give me 2x cubed minus 2x minus 2x cubed, all over x squared minus 1 squared, which ends up giving me negative 2x over x squared minus 1 quantity squared. Okay, now we have to find the critical values. So there are two types, first derivative equal to 0 and first derivative does not exist, but the function does exist. So still in the domain of f. So these are our two types. So for type 1, what we're going to do is set the numerator of the fraction equal to 0. So we get negative 2x equal to 0, which implies that x equals 0. Now 0 is in the interval that we're interested in. We're interested in the interval from -4 to 4. Closed on the left, open on the right. Now type 2, we're looking for where the first derivative does not exist, but the only places that the denominator would have a value of 0 are at 1 and -1, and 1 and -1 are not in the domain of the original function. So we have none of type 2. All right, so now we're going to set up a number line. The critical values become the separators on that number line, and we basically have to the left of 0 and to the right of 0. So we need some test points, but they have to be in the domain. So don't pick 1 and -1. That probably would not be such a great idea for plugging it into the first derivative. So instead, let's pick -2 and 2. All right, we want to pick something that's in the domain of the derivative. So our derivative is -2x over x squared minus 1 squared. Now, the denominator is squared, which means no matter what value we plug in, it's going to be positive. So all we have to worry about is the sign of the numerator. The sign of the numerator will determine whether it's positive or negative. So -2 times -2 is a +4. So a positive over a positive would be positive. And then again, looking at the domain, or rather at the first derivative, plugging it into the numerator, -2 times 2 would be -4. And -4 over a positive would still be negative. Now, I like to draw a picture that helps me think about what's happening. I basically have increasing behavior from at least -4 up to 0, since I'm only looking at that part of the graph. And then I have decreasing behavior from 0 up to 4, since we're restricting our view to just that interval, which means that I have a relative extrema here at the value that's in between. So I have a relative extrema at 0, and this is going to be a relative maximum because it goes from increasing to decreasing. So how do we find the relative maximum? We're going to take the original function and we're going to put 0 inside of it. So now we need to find the original function, which was up here. And this gives us 0 squared over 0 squared minus 1, which is 0. So our relative extrema is at 0, 0, and it's a maximum. Okay. Now, what we're going to do next is we're going to talk about concavity. But before we get to concavity, I want you to practice what we've been doing about extrema. So I want you to take this example and find the relative extrema, if any exist. Okay, let's take a look at it. This is one that we looked at earlier, but it's good practice for you to come through and try it on one that's difficult. So what we're looking at here is a polynomial function. The domain of the polynomial function is all reals. When you take the first derivative, you also get a polynomial function, and its domain is also all reals. So there are no type 2 critical points because this first derivative exists at all values. So we're looking for a type 1 critical point where the first derivative equals 0. Unfortunately, this one doesn't factor, so you have to use the quadratic formula. When you use the quadratic formula, you get 32/3 minus or plus 7 square root to 22 over 3. And that comes out to be about negative 0.2776 and 21.611. Now, the next thing we have to do is create a number line. So I use the decimal approximations of those to create the dividing points on the number line. So I have 3 regions because I have 2 critical values. So from negative infinity up to the first one, negative 0.2776. And then from that point up to the second one, 21.611. And then from 21.611 out to positive infinity. Those are our 3 regions. So we find test points, easy points, that will go into the first derivative. So they have to be in the domain of the first derivative. So I picked negative 1, 0, and 22. And I plug those values into the first derivative, which remember the first derivative is this value right here, the negative 3x squared plus 64x plus 18. Again, I'm not looking for the actual number. I'm looking for the sign. Is it positive or negative? So when I do that, I get a negative, then a positive, then a negative, which means it's decreasing over this first interval from negative infinity up to the first critical value. Then it's increasing between the first critical value and the second critical value. And then it's decreasing again from the second critical value to infinity. So the next thing that we want to do is evaluate where the extrema are. So if we have decreasing and then increasing, if you draw the picture, it's obvious. It's got to be a relative minimum. So we have a relative minimum here at this one. And it is a relative extrema. And then at the second one, it goes from increasing to decreasing. So it's got to be a relative maximum. And that's the second value. And then in order to find the y values of the extrema, I have to plug it back into the original function, not the derivative, which the first time I did it, I made a mistake and put it in the derivative. It has to go back into this function right here. So what are the different pieces of information that we got from doing this process? Well, first we have a relative minimum at this ordered pair and a relative maximum at this ordered pair. We can also state that it is increasing over the interval between 32 minus 7 square root of 22 all over 3 up to 32 plus 7 square root of 22 all over 3. So it's increasing on that interval. And it is decreasing over 2 intervals. So we have that information as well. So we know that the graph is going down over those intervals. So that would be from negative infinity up to the first critical value, 32 minus 7 square root of 22 all over 3, union from the second one to infinity. Oops, I started to write the decimal equivalent. 32 plus 7 square root of 22 over 3 to infinity. Now, the best way to plug these into the function is to store this value and then recall it as you work out the value of it in the original function. So you need to learn to use store and recall on your calculator. It is crucially important. The higher in math you go, the more important that is. And it is just so important in physics. If you have to take a physics class in the future, it's really, really important. Or if chemistry is in your future, you may need it in chemistry as well. All right. But for sure in the math courses. Okay. Now this is not enough information to really draw the graph, because remember, there are 2 ways of being increasing. You could be increasing like this, where it's concave down, or you could be increasing like this, where it's concave up. And that looks fundamentally different. I mean, there's a big difference between the 2 types of graphs. So just saying increasing is not enough. We need to know about concavity. So that's the next thing we want to look at now is concavity. And we're going to add to our example there. So concavity and points of inflection. What are points of inflection? Inflection is where it changes concavity. So you may have a concave down and a concave up, and that point where they connect is called the inflection point. So the inflection point is where the concavity changes or the curvature changes. So again, we've talked about the value of concavity, concave up being like this, concave down being like that. It is related to the second derivative. It's actually the rate of change of the first derivative. So the way we define concavity is by looking at the first derivative. And if you have a function and it's differentiable over the open interval I, so the derivative exists, if the first derivative is increasing, not the function, the derivative, if the derivative is increasing, so rate of change of the derivative over the interval, then we say it's concave up. So in other words, it's tilted uphill and more tilted uphill, all right? So that means that it's concave up. If we say that it's decreasing and becoming more decreasing, it's bending down. So if the first derivative is decreasing over the interval, we say that it is concave down. So in this way, we can say that because we're looking at increasing and decreasing behavior of the first derivative, we can use the derivative of the derivative in order to determine where it's increasing and decreasing. So the derivative of the first derivative is the second derivative. So when the second derivative is positive, we know that the first derivative is increasing, so it's concave up. When we know that the second derivative is negative, we know the first derivative is decreasing over the interval, so we know it's concave down. All right. Now let's take a look at a picture right here. So here are our pictures. In the first upper one to the left, we have that the first derivative is increasing. Now, what do we mean by that? Well, the derivative itself is the slope of the tangent line. So the slope of the tangent line is becoming steeper. Do you see that? They've got one orange line down here, which is less than a 1, and another orange tangent line a little further along on the x-axis where it is steeper than 1. So the slope of the tangent line is increasing. That means the first derivative is increasing. And because it's increasing, we know it is concave up. This means the second derivative is greater than 0. All right, so that's the piece of information that we're going to be adding to what we've already learned. We've already identified extrema and increasing, decreasing. Now we're adding concavity. Now, in this second picture, just like the first, the function is increasing over both. So that's another piece of information that we could add here. F is increasing here, and F is increasing here. The function itself is increasing in value. The first derivative, however, is decreasing. Even though the function is going up, do you see that the slope of the tangent line is becoming lower? It's going lower. I don't know how else to put it. It's decreasing. I'm trying to find another word for decreasing. It's not coming to me. So first we have a steeper tangent line. And then although the function continues to increase, it's not increasing at a rapid rate. And so that slope of the tangent line actually becomes less positive. It's still positive, but less positive. So the slope of the tangent line is decreasing in value, which means that the first derivative is decreasing and the second derivative is going to be negative. Right? So it is concave down. Now let's look at the two cases where the function itself is decreasing. So F is decreasing in both of these pictures. That means that the Y values are going down as X increases in both. But they are fundamentally different because the one on the left is concave up and the one on the right is concave down. Now, what causes that to happen? On the first one, it says F is increasing. And you may look at that and go, hang on, that doesn't look right. That tangent line is becoming less steep. And you're correct, it is. But these are negatively sloped. So this might be a -4 value of the tangent line. And this might be a -1/2. Well, which number is larger in value, -4 or -1/2? Think about the number line. -4 is to the left of -1/2. So -1/2 is actually larger. So the value in becoming less negative is increasing. So the first derivative is increasing, which means that the second derivative is positive and it is concave up. And the second picture here, the function is decreasing. And when we look at the tangent line, notice that they are negative again. And because they're negatively sloped, as they become more negative, they decrease in value. They go further to the left on the number line. And that's really what I'm talking about. Further to the left is decreasing on the number line, and further to the right is increasing, even if all the values are negative. So when I'm looking at this one, the first one towards the left side of the graph has a slope of maybe -1/2, but further to the right, it has a slope of -4. Remember to read the graph from the left to the right side. So as you're reading it, the slope of the tangent line is becoming more negative. So it's moving from here, more negative. Hopefully that went in the right direction for you. And I'm not mirroring my image, all right? So on my number line, hopefully that went the right way. That means that the first derivative is decreasing in value. And so its derivative should be negative, and that would be the second derivative. So F double prime is less than 0, and it is concave down. So this is the new bit of information that we're going to be adding. And this is the test for concavity. And then we're going to talk about where to find inflection points. So let F be a function that is twice differentiable. So what does that mean, twice differentiable? It just means that the second derivative is defined. So the first derivative may have places where it's not defined. And then if it's not defined there, you can't take the derivative again there. So we're looking at the domain of the first derivative and taking the derivative again. and then looking at that derivative and saying, where is it defined? So we've got a derivative in a domain and a domain and a domain. You really have to be careful. So we're looking at one that has a second derivative over an interval. And if the second derivative is positive, it is concave up. And if the second derivative is negative, then it is concave down. This is the same as saying that the first derivative is increasing or the first derivative is decreasing over that interval. Now, it can switch concavity, but when it switches concavity, this has to occur at a critical point. So it has to be a place where the first derivative or second derivative is undefined or the second derivative is 0. So these are critical values of the first derivative. Take the second derivative, set it equal to 0, or where is it undefined, but the first derivative is defined. So again, it's the same process we did the first time, but now applied to the first derivative instead of to the function. All right. So when we're looking at those values, those are called the inflection points. So if we have a function that is continuous at a point and it changes concavity there, then that point is called an inflection point. And that has to occur where either the second derivative is equal to 0 or the second derivative is undefined. Critical values of the first derivative. Okay. And we will be doing the same thing as we did the first. Okay, so let's take a look at all this information that we have on here. So over this section from, well, I don't really have names for everything. So let me put some more names up here. It only has A on the graph. So let me call this B and I'll call this C. So from A to B, the function is decreasing, going downhill. That means the first derivative is negative. That's what tells you it's decreasing. It's also concave up. We can tell that because the slope of the tangent line is becoming less negative. It's negative here, and then it becomes flatter, which actually increases in value. So the second derivative is positive, which means it's concave up. So it's concave up on this section between, well, I guess we'd call it 0 to B. And then between B and A, the function is increasing, which means the first derivative should be positive because it's increasing. That's what the first derivative does. Now let's look at the tangent line. It was flat, which is 0. Then it became a little positive, like 1/5, then 1/2, then 1. So it looks like it's increasing in value, which means that the second derivative is still positive. So the tangent line, the slope of the tangent line is moving to the right towards larger numbers. And so the second derivative is still positive, which means again that it is concave up. You can, of course, just look at it and tell it's concave up. And then at point A, we have an inflection point. An inflection point is the precise value where it switches concavity. It goes from concave up to concave down. This is going to be where f double prime at A equals 0, or f double prime at A does not exist, but f prime of A does exist. All right, so we're just taking it one derivative past what we've been doing, but it's applying the same steps, finding critical values of the first derivative. In the next section between A and C, we can see that the function is increasing still. But, so because it's increasing, the first derivative is positive. But let's look at the slopes of the tangent lines. They start out fairly steep and positive. So numbers like 4, and then 3, and then 2, then 1/2. They're getting lower. They're moving to the left on the number line. And because they move to the left, they're decreasing. So the second derivative is negative, which means it's concave down. Right? Now, what about from C out to, well, we'll just call it D over here, C out to D. When we're looking over here, the function itself is decreasing. So the first derivative should be negative, and it is. And then we look at the slopes of the tangent lines. It starts at 0, and then it tilts a little negative. So -0.5 near 0, and then -1, then -2, then -3. It's moving to the left on the number line. So it is decreasing. So the second derivative is negative, which makes it concave down. Okay. Now, when we're talking about position time graphs, which you have on your exam coming up tomorrow, the inflection points are where the acceleration is 0. Why? Because acceleration is the second derivative. So the inflection point is where the acceleration is 0. That's where you pulled your foot off the gas, but you haven't put it on the brake. You're not accelerating or decelerating. The acceleration is 0. All right. Let's take a look at this example that we were looking at before, and let's add the concavity piece to it. So we want to find all the intervals where the function is concave up and all the intervals where it is concave down. So we've already got the information about where the relative extrema are. What we want to add to it now is where the concavity changes and where it's concave up and concave down. So we're going to start again with the first derivative, and we're going to copy that off, and we're going to look at the second derivative. So we're going to repeat the process that we've already done on the first part. We're going to repeat it on the first derivative. So here's the first derivative. Now we need to find the second derivative. Oops. F double prime, which is going to be a -6x plus 64. Now we find the critical values of the first derivative, which would be where the second derivative equals 0. This is a type 1, or type 2. The second derivative of x does not exist, but it's in the domain of the first derivative. So it's exactly the same process we did the first time, just repeated on the first derivative. So now what we do is notice that the first derivative has a domain of all reals, and the second derivative has a domain of all reals. So there are no type 2 critical values. The second derivative always exists. So where does the second derivative equal 0? Take your -6x plus 64, set it equal to 0. So you get 6x equals 64, or x equals 64 over 6, which is 32/3, which is 10 2/3, or 10.6 repeating. All right. What is that? Well, that's where the second derivative is 0. So it's the point between, it's the inflection point. Now, how do we find the true value of the inflection point? To find the true value of the inflection point, the ordered pair, we now need to take this 32/3 and plug it into the original function, not the second derivative, not the first derivative, the original function. So moving way up here, we're going to need to plug it into here to find the inflection point. And I should get the whole thing. Now that's only if it changes sign at that point. So we need to check and see if it changes sign. So to check and see if it changes sign, what we're going to be looking at, of course, is the first derivative, where the first derivative changes sign. So now coming down here, we create some more space. Looking at this one, we create a number line and we have a point that divides it, which is 32/3. And I need to pick a number to its left and a number to its right. You don't have to pick the number right next to it. You can pick any number you want as long as it's in the domain of the previous derivative, which in this case would be the first derivative. So I'm going to pick 0 since 0 is to the left of that, and 0 is always one of the easiest numbers to plug in. And then 11 would probably be the next number out, which is 33/3. Now I need to know about the sign of the first derivative, all right? Not the function, the sign of the first derivative. So is it increasing or is it, or not the first derivative, the sign of the second derivative. So when I'm looking at the sign of the second derivative here, is the second derivative positive or is the second derivative negative? So when I plug these values in and I take my test points, it looks to me like if I plug it into the second derivative, which is up here, I get a positive value, which tells me that it's concave up in this section, all right? Now I plug in the 11 into the second derivative, or 12 or whatever number you picked. It's got to be larger than 10.6 repeating. So when we plug that in, I get a negative value, and that tells me it's concave down. So the information that I've added is that it's concave up over the interval from -infinity up to 32/3 on the x-axis, and it's concave down over the interval from 32/3 to infinity. And I have an inflection point which is at 32/3. And now I need to take 32/3 and plug it into the original function. So the original function, creating a little more space than I anticipated. There's my original function. So f of 32/3 is negative times 32/3 cubed plus 32 times 32/3 squared plus 18 times 32/3. You will definitely want to have a calculator that you are comfortable using for the third exam, because these require a lot of calculator use. So we'll have a -1 times 32. Let's back up, put that in parentheses. 32 divided by 3, close parentheses, cubed, plus 32 times parentheses 32 divided by 3, close parentheses, squared, plus 18, open parentheses, 32 divided by 3, close parentheses. I got, in decimals, I also got an exact fraction, but we'll do it in decimals. 2,619.26, rounding off. If you want the fractional part, I think a mixed number is better in this case, 2,619 and 7/27. That's where the inflection point is. Okay. Now, this is a good example of why we do this work analytically, meaning by hand. What are the chances that I would know that I needed to extend the axis in the y up to at least 2,619? None. I probably wouldn't normally go that high, but this tells me where it is, so I know that I've got to look there. And previously, we found where the relative minimum and relative maximum were, and this was at 5,241. So for example, if I want to get all the pieces of information that I found so far on this graph, I know that my domain should probably extend from at least, let's say, -5 up to 25. And for the Y values, I should go from -5 to at least 5,300. So let's go over here and put that in onto our graph and take a look at what it looks like. So we've got -x cubed. And I've forgotten, plus 32x squared plus 18x. Plus 32x squared plus 18x. All right, now I'm not seeing all of the graph. I'm missing huge chunks of it. Again, you have to do it analytically so you know what's critical and where you need to include values. So I said that I probably need to go from about -5 up to 25. So I'm going to change that to -5. And I'm going to take this up to at least 25. And for the Y values, I said I probably need to go from at least maybe -5 up to 5,300. Haha. Now we have a much better picture of what the graph looks like. And now you can actually see the cubic behavior, whereas the first time I graphed it, it looked more like a parabola. But now I can see the critical values that came about and created this graph. So Desmos is very good about locating the minimum value, which is right here at that particular point. And then it's at -0.278, which is about what we found. And we've got the -2.509, which is what I found. And then up here, we've got the relative maximum, which was at about 21.611. And there's the Y value, 5,241.03, which matches what I found. And then somewhere in between here, we have an inflection point. And I'm trying to remember what we found the inflection point to be. What did we find the inflection point to be? 32/3. So 10.666 repeating. So very close to there. All right. So very close to there. And that's 2,613, which is going to be very close to 2,619. So we could do 32/3 as a point on the graph. And then it was 2,619. And I don't know if it'll do this, 7 divided by 27. Yep, it did take it. That's where the inflection point is right there. And you can tell that, yeah, that looks about right. That's where it changes from being concave up to being concave down. So we do have this change in concavity. We've got the decreasing behavior over this interval up to here, and then again from the second critical value down. And then we've got the increasing behavior between the two. We can use our college algebra skills to find the x-intercepts. Remember, to find x-intercepts, you set the original function equal to 0, not the derivative, the original function. Remember your college algebra, don't freak out. That's where the Y value is 0. So we could find those points as well. So we're building pieces of information to get what the graph should include so that we can see all the important pieces of information. Okay, let's take a look at another example. This is going to be example number 5. And this one is a natural log. Now, natural log are always somewhat interesting functions, and they're typically a little different. As far as graphing goes, they tend to be a little easier, actually, because they tend to not change their concavity too much. So let's take a look at what this one does. Now, it does have an argument with a power in it, 3x squared, and that may change the concavity of it somewhat. So to find concavity, and that's all we're looking at first, to find the concavity, you want to look at concave up and concave down. So you're looking at the second derivative. We'll go ahead and do the first derivative material as well, but we're really looking at the second derivative is what we're primarily interested in, but we'll do all of it. Okay, so we have our function, f of x equals the natural log of 3x squared plus 1. And we need to think about the domain. Now remember, for natural log, you take the argument, you pull the argument out, and you say you have to be strictly greater than 0. It cannot equal 0. Now, 3x squared plus 1, since it's squared and they're positives, then it's always going to be positive unless it is 0. Is there a way to make it 0? Well, the only way to get it to be 0, since I have a plus 1, is if 3x squared came out to be -1. But that's not possible because it's a positive 3 times an x squared. So this can never be 0, and it will always be strictly positive. This is important because it means the domain is actually all reals. All right. Now, if you're not sure, what can you do to help reinforce that, yes, you do have the right domain? What could you do?
Put a negative number.
You could plug in numbers and test it. That's a great idea, plugging in numbers to test. How about just graph it and look at it? Natural log of 3x squared plus 1 equal y. Okay, now why is it looking like a horizontal line? We know it's not a horizontal line. Why is it looking like one? Do some troubleshooting for me. What does natural log normally look like? Kind of comes up and then it moves out like this. What's wrong? Check your scale, people. What's your scale?
We're still stuck
Huge
on the
numbers.
last function.
Yeah, Caleb's right. We're still using the old scale, which goes up to 5,000. Natural log is the slowest growing function that we have. Of all the functions that do go to infinity, eventually it gets there slower than anybody else. It's so slow. So of course it looks like a line because it's growing so slowly. Hit the house to go to default zoom. And now you have a much better picture of what it actually looks like. All right. And you can see the behavior of it. Now, if you're tempted to think, oh, maybe it's not really defined at 0, you can click on it and notice it does have a value 0, 0. It is defined there. If it were not defined, Desmos would say undefined. All right. So it's defined everywhere. All right. Now we want to take a look at the first derivative. So we're going to do f prime of x. We're looking for critical values or critical points. So f prime is going to be the derivative of natural log is 1 over u du dx. So times the derivative of 3x squared plus 1. This is chain rule. So 1 over u du dx. That's the formula you need to memorize. So this is going to give us 6x over 3x squared plus 1. So that is our first derivative. Notice that the domain for the first derivative is going to be a subset of the domain of the original function. The original function is all reals, and the domain of the first derivative is also all reals, because there's nothing that will make that denominator 0. It's not possible. 3x squared is always positive. It can't equal -1. So the domain of the first derivative is also all reals. So now what we want to do is we want to look for our type 1s, because since the domain is all reals, there are none of type 2, because that would be first derivative does not exist, but in domain of f of x, and all of them exists. So it exists everywhere on all reals, right? So f prime always exists. So we have none of type 2. Type 2s are relatively rare. I see them most of the time when you have a square root or a cube root in the original, and you take the derivative and puts it in the denominator. That's typically where you'll see a type 2 coming in. All right, so our type 1s are f prime of x equal to 0. So that means take the numerator of the fraction, the rational function, and set it equal to 0, which implies that x equals 0. Okay. So now we're going to take a look, get that down to the next page. I know I'm going to need a lot of space. We're going to take that critical point and we're going to divide up the real number line in values to either side of it. So I'll take a test point that's in the domain of the original. So the sign of f prime. So I'm looking at f prime here. Really, I'm looking at the sign of f prime. So a test point would be -1 and 1. And I'm looking in the first derivative, which is 6x over quantity 3x squared plus 1. So a negative in the top would make it -6. The bottom is always positive. So that makes it negative. Again, I don't care about the number. I want the sign, positive, negative. Then when I plug in 1, I get a +6 over a positive, so it's positive. So this gives me the following information. It's decreasing and then increasing. So I have a relative minimum at 0. I need to find the y value there. So I'm going to have to go back to the original function, which is right up here, and I'll have to plug that in to find the y value at that relative minimum. All right. So copying off the original function, then I can find f of 0 is equal to the natural log of 3 times 0 squared plus 1, which is the natural log of 1, which is 0. So I have a relative minimum at 0, 0. And I also know that it is decreasing. That function is decreasing from -infinity up to 0. And it is increasing, going uphill from 0 to infinity. So those are the pieces I can get from the first derivative test, right? Now we want to apply the second derivative information, which is about concavity. So we need to take the derivative of the derivative. So that was 6x over 3x squared plus 1. So now we want to find the second derivative. First derivative was 6x over 3x squared plus 1. I think you can do it either way. I don't really have a preference. I do tend to sometimes just use the quotient rule, but if you hate the quotient rule, keep in mind that you can always turn it into product rule. It would just involve the chain rule. So you got to be really good at the chain rule in order to do that. So either way, whichever way you prefer, let's take the derivative of the first derivative to get the second derivative. So our second derivative is going to be 6 times 3x squared plus 1 minus g prime 6x times 6x g prime f all over g squared. So that's giving me 18x squared plus 6 minus, 36x squared. You guys check my algebra. Keep me honest. That's your job. My job is to guide you. Your job is to make sure I don't make careless mistakes. So -18x squared plus 6. over 3x squared plus 1 squared. So that's the second derivative, right? Now that we have the second derivative, we want to go ahead and find out where the critical values are. So when we're looking at the critical values, we need to go ahead and see where the second derivative is either 0 or the second derivative does not exist, but the first derivative does exist. So now we're looking for critical points of the first derivative or the second derivative, however you want to put it. So type 1, second derivative equal to 0. So that would be the numerator, negative 18x squared plus 6 equals 0. And when we work that out, we're going to get 18x squared equal to 6. Divide both sides by 18. So I get x squared equals 1/3. And then take the square root of both sides with a plus or a minus, since you don't know with the sign of it. And I get plus or minus 1 over the square root of 3, right? Type 2s would be where the second derivative does not exist, but it is in the domain of the first derivative. So this would be second domain does not exist, but in domain of f prime. And the second derivative is never going to have a denominator of 0 because we've got that 3x squared plus 1 again in the denominator squared. It's never 0. So there are none of type 2 again. Again, type 2s are relatively uncommon. I'm not going to say rare, but they are definitely uncommon. So there are none of type 2. Okay. So now we've got our values right here, negative 1 over the square root of 3 and 1 over the square root of 3. So we want to create a number line again. And this time we want to look at the sign of the second derivative. And we're looking at negative 1 over the square root of 3 and positive 1 over the square root of 3. So in between, a good test point would be 0. Now, I don't know exactly what 1 over the square root of 3 is, but maybe that would be helpful. 1 divided by the square root of 3. It's about 0.58. So a good test value here would be negative 1, which is below it, and a good test value here would be 1, which is above it. So the next thing I'm going to do is evaluate at those test points. And this time I'm looking at the second derivative. So let me copy off the second derivative, negative 18x squared plus 6. All divided by 3x squared plus 1 squared. I think that's correct. Okay, so plugging negative 1 in, note the denominator squared. Don't even pay any attention to it. Don't bother trying to plug in. It's squared. It's got to be positive. So only the numerator affects us. So when we plug in negative 1 squared is 1, but multiplied by negative 18 is a negative 18 plus 6. So it's a negative over a positive, so it's negative. So we have a negative down here. When we plug in 0, we have 0 for the first term, 6 for the second. So we have 6 over a positive, which is going to be positive. And then we plug in 1, we're going to get the same thing we got when we had negative 1. It looks like it might be symmetric across there. So this is going to be concave down over this interval and this interval, and concave up here in the middle, which means that we have 2 inflection points. So now we want to include this information. So we have it concave up over the interval from negative 1 over the square root of 3, which again is about negative 0.58, to 1 over the square root of 3, which is about 0.58. And it's concave down between negative infinity up to negative 1 over the square root of 3. And again, between 1 over the square root of 3 to infinity. Right? So we're looking at all these pieces of information. Now we need to know where its inflection points are. Inflection points are on the original graph. So we want to come back up here to this original function, and we want to evaluate the y value at the inflection points. So we'll put the original function back in here, and we'll find the y value at the inflection points. Okay, so plugging in, we have f, oops, it's not wanting to write, f of negative 1 over the square root of 3, which is going to be equal to the natural log of 3 times negative 1 over the square root of 3 squared plus 1, like that. Now, because it's squared, it's actually not going to matter if we have negative 1 over the square root of 3 or 1 over the square root of 3. When we square them, they both become 1/3. So this, in fact, is going to also be equal to the value of f over 1, or f of 1 over the square root of 3. They'll be identical. So this is going to give me natural log of 3 times 1/3, which is 1, plus 1, which equals the natural log of 2. So now I have an inflection point at negative or plus or minus 1 over the square root of 3 natural log of 2. So let's put that information in over here on our graph. Plus or minus 1 over the square root of 3 natural log of 2. So negative 1 divided by the square root of 3, comma, natural log of 2. Oops. I always manage to get the commas and the quotes in the wrong place. Ew. Okay, let's start over. That didn't work out right. 1 divided by square root of 3, move out, comma, natural log of 2. There we go. We'll label that. We'll copy it, paste it again, and take the negative off. We'll make it blue to match. All right. So we've got our 2 inflection points there. So the inflection points change from where it's concave down to concave up, from concave up to concave down again. So we've got our inflection points. Notice that it is decreasing from negative infinity to 0 and increasing from 0 to infinity. We found that with the first derivative test, which was up here. Decreasing from negative infinity to 0, increasing from 0 to infinity. And we have a relative minimum at the origin at 0, 0. So we can also put the relative minimum on the graph. So we have a relative minimum there. And then we have our changes in concavity. All right. And that would allow us to draw a pretty good graph, a pretty good estimation of what it looks like. All right. A really good estimation of what the graph looks like. Let's do the summary of the information that we have. We may skip example 6 and go on to the second derivative test. If the sign of the first derivative is positive, it's increasing. And if the sign of the second derivative is positive, it's concave up. If it's negative, it's concave down. If the sign of the first derivative is negative, it's decreasing. And then again, concavity is determined by the second derivative. All right. So in the example 6, we're just looking at graphs and we're determining where it's concave up, concave down. I believe that's all it asked for. Oh, increasing, decreasing, concave up, concave down. And what does that indicate about the signs of the first and second derivative? So we'll do one of these and then we'll go on to the next. So I'm going to divide it into regions like from here to here and somewhere here up to here and here to here, then to here, then to here, then to here. Why am I dividing it at these places? Why am I choosing these places to divide it? Why are those my division points? What am I looking at? Relative minimum, relative maximum, and inflection points. That's what I'm doing. The critical values of the first derivative and the critical values of the second derivative. So if I look at this one right here, the first derivative has to be negative because it's decreasing. It's concave up, so the second derivative is positive. On the next section, it is increasing, so the first derivative is positive. Second derivative is also positive because it's still concave up. In this section right here, the first derivative is still positive because it's still going up, but the second derivative is now negative because it is concave down. In this tiny little section right here, it's decreasing. So first derivative is negative, concave down, second derivative is negative. All right, does everybody see kind of what I'm doing? Are there any questions about how I'm doing that? Okay, all right. In this next section right here, I'm kind of running out of space. It looks like it's still decreasing. So first derivative is negative, but it's concave up. So second derivative is positive. And this region next to it, on the other side of the relative minimum, it's increasing. So first derivative is positive. It's concave up. So second derivative is also positive. In this section right here, it's increasing. So first derivative is positive, but it's changed to concave down. So second derivative is negative. In this region, it's decreasing. So first derivative is negative. It's concave down. So second derivative is negative. In this piece, we have decreasing. First derivative is negative. Concave up. Second derivative is positive. Over here, we have increasing. First derivative is positive, and it looks like it's still concave up. So second derivative is also positive, all right? So I could give you something like this and say between A and B, tell me about the sign of the first and second derivative. The first derivative is positive or negative. Second derivative is positive or negative. And then ask you, what does that mean? Increasing, decreasing, concave up, concave down. All right. Okay. Let's talk about the second derivative test. We've used the second derivative to find concavity, but that's not actually the second derivative test. The first and second derivative tests were designed to tell you where the relative extrema are. So the second derivative tells us where relative extrema are. The difference is the first derivative test always works. If it goes from decreasing to increasing, it's a relative minimum. If it goes from increasing to decreasing, it's a relative maximum. That's the first derivative test. The second derivative test says, if you are looking at a particular function And the first derivative is 0. So this does not include the type 2s, where the first derivative does not exist, but the function does exist. Doesn't include type 2s, which are relatively uncommon. So it picks up the more common case where the first derivative is 0. And if the second derivative is continuous over the interval, meaning that it's defined there. So if the second derivative is positive, concave up, then it has to be a local minimum. And if the second derivative is negative, it's concave down, has to be a local maximum. And if the second derivative is 0, then we have no idea. And that's the part where it fails. Inconclusive is math way of saying, I have no idea. Go back and try something else. That's what it means. Inconclusive, can't tell, do something different. All right. And the something different is the first derivative test. So what is this saying? This is saying if you've got a critical point on the function, so the first derivative equal to 0, and you know it's concave up at that point, so you know it's curved like this, and you know that point is a critical value. Well, look at the picture. Doesn't it have to be a relative minimum? I mean, what else could it be? On the other hand, if you know it's concave down, and you know that point is a critical value where the first derivative is 0, it has to be a relative maximum. The only problem is you can't tell if the second derivative is 0. It might be a relative minimum, it could be a relative maximum, or it could be a saddle point, in which case there's no relative extrema. You have to go back to the first derivative test. So let's take a look at example 7. Consider this function here, which is a polynomial function. So our domain is going to be all reals. And the points 3, -2 satisfy the first derivative equal to 0. So I've already given you the critical values. There are no critical values that come from type 2. Remember that the first derivative on this one, if we want to do it real fast, would be 3x squared minus the 2 would cancel the 2 in the denominator. So I'd get minus 3x minus 18. So there are no type 2 critical values. Right? And they went ahead and did the type 1s where the first derivative is equal to 0, and they got x equal 3 and -2. And now we want to use the second derivative test to determine whether they're maximums or minimums. So instead of dividing up the number line by the 3 and the -2 and using test points and testing the sign of the first derivative, what we do instead for the second derivative test is we find the value of the second derivative. So f double prime, which would be 6x minus 3, and we plug in the value of the critical points. F double prime of 3 would be 6 times 3 minus 3, which is 15, which is positive. So it's a relative minimum. So it's faster. It's a much faster way of determining if it's a relative extrema. What's the downside then? It doesn't always work, right? If you get 0, it failed and you've got to go back to the first derivative test. So then you can test the other one. Second derivative at -2, which is 6 times -2 minus 3, which would be a -15. So it's negative. That's what we care about. So it's concave down. So it's got to be a relative max. So concave up and concave down. So it's got to be a relative max. That's it. That's all it says. It doesn't tell you where the y value is. If you want the y value, you still have to go back to the original function and plug 3 into the original function to get the y value, or -2 into the original function to get the y value. It only gives you the x values where those occur. So the second derivative test worked on this one. It's faster than doing the little test points and determining the sign of the first derivative, but not by a whole lot. I'll be honest with you, I don't often use the second derivative test. Okay, I shouldn't say that, but I really don't, because of the disadvantage of getting 0 where it fails to work. Okay. All right. And then the only other one we have here is this natural log of x times the square root of x, where we're going to go through and find all possible values. So let's take a couple minutes and look at this one quickly. So we have the function equal to the natural log of x square root of x. Now, x and x square root of x can be written in power form as the natural log of x times x to the 1/2, which can be written again as the natural log of x to the 3/2 power. Now you could pull the 3/2 to the front of the natural log, but that changes the domain a little bit. So I would leave it where it is. First off, that x to the 3/2 has to be greater than 0. So the domain of the original is going to exclude 0 and it's going to exclude negatives. So the domain is going to be from 0 to infinity. All right. So we're not going to be looking at anything outside of 0 to infinity. That's the first thing. Find the domain of the original. Then we can find the derivative. So we do the derivative of the function. The derivative of natural log is 1 over u du dx. So times the derivative of x to the 3/2. That's chain rule. And then we will write this as 3/2 x to the 1/2 over x to the 3/2. All right, so that would become that. Now, 1 over u du dx. So this is our derivative, but we can clean it up because we have x to the 1/2 and x to the 3/2. So if I drop this down, it's 3/2 minus 1/2, which gives me an x. In other words, the square root of x cancels. And this becomes 3 over 2x. That's the final value for that one. Right? When you're looking at the derivative of that one. Okay. Which is doing it a slightly different way. Now, if you had not taken the time to simplify the argument to the natural log, you would have had to use the product rule and would have made your work a lot harder. So in general, do a little bit of algebra, then do calculus, then a lot more algebra, right? So most of calculus is algebra. So now we're looking for the type 1s and type 2s. Type 1, we're looking for the first derivative equal to 0. Uh-oh, something has gone awry. When I simplified it, I lost some information. Oh, okay. I misinterpreted the function. So let's start with this one tomorrow. If we continued with this one as it is, the way I've interpreted it, this type 1, there would be none, right? Because 3 does not equal 0. And type 2, the only one we would have would be x equals 0, but that's not in the domain of the original. So we have none here either, which means we have no critical values. All right. So we could look for concavity. Basically, this thing is going to be all one way or the other. Since our domain is 0 to infinity, it's basically always increasing. All right. If we plug in values, we would get that it's increasing on 0 to infinity. We can also take a look at the concavity behavior. So to do that, we need to take the second derivative, which we apply to the first derivative. I'm applying it in this form right here. So after I've simplified it, so I have 3/2 x to the -1.
So pull the -1 to the front, times 3 has x to the -2, which causes the x to the -2 to drop to the denominator. So you get -3 over 2x squared. Now 2x squared is going to be positive for all values of x. Since 2 is positive and anything squared is going to be positive, it won't be 0. Plus 0 is not in the domain anyway, so we can ignore that. We're only looking at the domain of 0 to infinity. So since the denominator is always positive, the numerator is always negative, it's always going to have a negative second derivative. And that's going to mean that it's concave down everywhere. So basically, we have an increasing function, so it's going uphill, but it's curved down. So it's coming up like this and moving out that way. All right. Now, in the next video, we'll be taking a look at putting all of this information together and doing as much as we possibly can to describe the graph. And the reason we want to do this is because we need to know where the important parts of the graph are. If there's something happening at 150, x equal 150, but I only graph between 100, -100, and 100, I'm going to lose that information. So we want to make sure that we have all of the pertinent parts of the graph on the graph. So we need to check and make sure that all critical values and inflection points, maxima and minima, x-intercepts, y-intercepts, are included in the x range, and that the y range also includes the values for the maximums and minimums on the graph. So in the next video, we'll work several examples where we look at absolutely everything: x-intercepts, y-intercepts, holes in the graph, vertical asymptotes, oblique asymptotes, increasing behavior, decreasing behavior, concave up, concave down, relative maximums, relative minimums, inflection points, saddle points. We're going to look for all of it in the next video.